Okay, so for the last couple of days we have been discussing about the magnetic field, doing some examples. Just to give a summary, we know that the magnetic field created by a line charge, it can be written as an integral of I times dl cross r minus r prime divided by r minus r prime cube, this dl vector. So which is basically, this is the magnetic field at the point r. So this is the wire we have. It carries a current I. So if we just take a very small segment of this wire, define this vector dl vector along the wire in the direction of the current, and it has the length is equal to the length of the segment, so that we will denote the position of that as the point r prime, and we are looking at the magnetic induction at the point r. Which, if we have a volume current instead of just a current carrying wire, I mean the charges need not flow along a wire, they can be just flow in any, even in vacuum you can have a flow, a motion of charges, which can be written as a current density. We will have a volume current density. This is the same as 1 over c times the integral over the volume, let me put the prime index, times j at the point r prime cross r minus r prime over r minus r prime cube. And just, well, these are just experimental observations. Now, starting from these expressions, we had shown that we can write, in fact, the B field as the curl of 1 over c times dv prime j of r prime over r minus r prime, which we defined as the vector potential. This is A. And so since the magnetic field is equal to the curl of this vector field, its divergence is automatically zero. So which basically tells us that there are no magnetic charges. Magnetic field lines, when you draw them, they cannot start or they cannot end at a given point. They have to form closed loops, or they can go to infinity, which basically tells us that they are closing at infinity. And if we just calculate the curl of the magnetic induction, what we obtain is 4 pi over c times j. And in fact, if you just, up to now we started with this experimental observation, and from which we derive these two equations that the magnetic induction should satisfy. Now we can also go the other way around, so these are our new Maxwell's equations describing the magnetic induction. Now this divergence of B being equal to 0 just tells me that B, I can always write it as the curl of some vector field, A. But the thing is, for example, if you just replace A by, let's say, A plus the gradient of some function, scalar field, let's call this A prime, curl of A prime is equal to curl of A plus the curl of divergence of lambda, but the curl of the gradient of lambda, sorry, but the gradient is always, the curl of a gradient is always 0, so the curl of A prime is equal to curl of A, which is equal to B. So this basically tells me that for a given magnetic field, the definition of A is not necessarily unique. There are infinitely many of them. You can think of this as, in the case of electrostatics, we had this freedom of adding a constant to the potential. We could always shift the potential by a constant. Now we have a larger freedom over here. We can just add to the vector potential any gradient of any function. So there's no unique, there are infinitely many vector potentials corresponding to the same magnetic field. So this is a freedom we can use, just like in the case of electrostatics, we had the freedom of choice of the value of the potential at a given point. we usually chose that point to be at infinity and the potential at infinity to be 0. So here we have this freedom of adding to our vector potential any gradient of a function, gradient of any function. Now, if you write B as the curl of A, then the curl of B, this is equal to, curl of A, which is the curl of B, this was equal to the gradient of divergence of A minus the Laplacian of A. This should be equal to 4 pi over C times J. So we have both of these terms. But now remember, I have the freedom of changing the definition of A. I am free to choose the A such that the divergence of A is 0. So let's see, let us do this for A prime. So we have one A, which doesn't necessarily have 0 divergence. Let us make a change to A prime by adding the gradient of lambda. Then is it possible to find this lambda? That's kind of the question. Well, let's see. Divergence of A prime will be divergence of A plus the Laplacian of lambda. We want to choose a lambda such that this is equal to 0. Or Laplacian of lambda should be equal to the minus the divergence of A. Well, this is what we are studying. We have B, a given B. We found A, which doesn't have a 0 divergence. Now I'm just asking, is it possible to choose lambda such that A prime has 0 divergence? To find such a lambda, I have to solve this equation, this Poisson's equation. So A is known, the divergence of A is known. If I can solve this Poisson's equation, then I can determine A prime such that the divergence of A prime is 0. But the Poisson's equation always has a solution. So I can always find this lambda. So I can always choose a vector potential such that its divergence is 0. Such that the divergence of A prime is equal to 0. But if the divergence of A prime is equal to 0, let's say this term I can always make 0 without changing the B field. I only have the second term, so Laplacian of A is equal to minus 4 pi over C times J. Now let me put A prime. And I will just drop the prime. So from now on, whenever I assume I am talking about a vector potential, I will implicitly assume that the divergence of that vector potential is 0. So that's an additional condition we impose on the system. It doesn't come from the expressions for the B fields. The A, there are infinitely many of them. I'm choosing a particular one which has 0 divergence. This is called a gauge fixing. This is called Coulomb gauge. And this is an example of a gauge transformation. So instead of one vector, so we have these family of vector potentials which correspond to the same B field. So in a sense, physically they are equivalent, they are identical. And I can use any one which pleases me. Well, if this, we already know how to solve such an equation. You see the x component of A satisfies minus 4 pi over C jx, similar to for y and the z components. Well, this is just like the electric potential. And we already know how to solve the electric potential. The right-hand side just looks like the charge density. So A, x, y, or z will be equal to 4 pi over, 4 pi's integral over the volume V prime j of x, y, or z at the point r prime divided by r minus r prime. Well, I have also the c. Well, this was the expression we had also obtained previously. But keep in mind, on purpose, I'm using the Cartesian coordinates over here. A phi, for example, if you look to spherical coordinates, A r, phi, or theta, this is not equal to dv prime j of r, phi, or theta, r prime over c divided by r minus r prime. This is not equal. The equality only holds for the x component equal to the integral of the x component of j, the y component of a is equal to the integral of the y component of j, etc., only in the Cartesian coordinates. Basically, because how do you calculate the phi component? This is a dot phi hat, which is equal to dv prime j at the point r prime phi hat divided by r minus r prime 1 over c. Now j r prime dot phi hat, remember this phi hat is at the point r. This is, since this is at the point r, this is not equal to j r prime scalar product with phi hat at the point r prime, which is j phi at the point r prime. So the phi vector at every point is a different vector. So that is why we cannot write the phi component of the vector potential as an integral over the phi component of the current j, the current density, because phi component is a different thing at every point. But the x component of a vector is the same at every point. It's the same direction. Whether this, if this is your x hat vector, it is the x hat vector at this point, it is the x hat vector is this one at this point. But at this point, the phi hat vector is, let's say, in this direction. At this point, the phi hat vector is in this direction. So it's a different vector at every point. Now we will do some applications of the calculations of B and the A. Now let's look at the example of the Helmholtz coils. Do you remember Helmholtz coils? Well, at least you did the experiment with Helmholtz coils. You didn't do. So the idea is, for example, we are talking about uniform magnetic fields. How do you create uniform magnetic field? Now, it will be an approximation, and the best approximation we have is what's called the Helmholtz coils. So let's see, these are, let's assume you have a ring of current carrying ring over here. It will create a magnetic field, let's say, along the center in this direction. The magnetic induction. Well, you put another coil over here. It also runs current in the same direction. So if you would just show the magnetic induction lines, so here it's coming out, here it's going in the current. The magnetic induction lines will just basically, now if you are very close, they will just go like this. As you go away from very close to the wires, they will start more or less going like this. They will just wrap both of them. Along the center, they will be just straight. So at this middle line, the magnetic field lines are basically perpendicular to the surface, to that middle surface. That is something we want. And we will just study what is the magnetic field in this region, close to the center. How does it, let's say this is our z-axis. How does it change? This is z is equal to 0. How does it change with z close to z is equal to 0? That's what we would like to see. And we will try to find some range of parameters. Let's say this is the radius r, and they are separated by a distance d. So for what values of r and d, that region over there is almost uniform. So that is what we will be trying to calculate. No. Well, so is the side of that ring containing the arrow, is it close to you or further away? How do you see it? No, it's this one. You see, the loop is like this.
Okay.
So this side is the further away side. This is the closer side. Yeah, these are one of the optical illusions which I don't know how I would avoid it. Further, the problem is I'm left-handed. Probably you would have drawn it the other way around. For example, I make checks like this. A right-handed person makes checks like this. For me, a cube is this one. For a right-handed person, a cube is this one. If you are not sure about the direction of things, ask me. Well, okay, so this is what we are interested in. We would like to look at the magnetic field in this region. And we would like to have it as flat as possible, as independent of z or any other coordinate as possible. Well, to do that, let us just consider one of the rings. Well, this ring is basically equidistant from both of the rings. So the magnetic field at that point would be the magnetic field created by one of the rings multiplied by 2. So let's look at that problem first. So we have our ring. And at the center, at a distance d over 2, we have a magnetic field. We would like to find the magnetic field at that point. And there is a current I running through it. Now we will be basically using the Biot-Savart law, which states that the magnetic induction created by a current carrying loop is the integral over the loop of dl cross r minus r prime divided by r minus r prime cubed. That's the integral we need to evaluate. Now let's look at a segment over here. dl is this vector. Or let me, to make it easier to see, let me take this segment. This is my dl. That dl is into the screen, actually. If you just look at it from the side, it's into the screen. Now this vector is r minus r prime vector. And they are perpendicular to each other. Because dl is into the screen, and that r minus r prime vector is on the screen. What is the direction of dl cross r minus r prime? Into the screen, r minus r prime is somewhere like this. So this is the direction of dl. This is the direction of dB. Now I will consider the diametrically opposite segment, this one. Let me call it dl prime. Now dl prime is pointing towards you. And again, this time this is my r minus r prime for that segment. And again, that vector is in the screen. So these two dl prime vector and that r minus r prime for dl prime is perpendicular to each other. So what is the direction of dB from that segment? On the other side. This angle is equal to this one. We have dB prime over here. Now dB magnitude, what is the magnitude of dB? It's 1 over ci dl divided by r minus r prime squared times sine of the angle between dl and r minus r prime. That angle is 90, sine of 91. So this is the magnitude of dB. But this is also the magnitude of dB prime. Let me call this one capital D, that length. I over c dl over d squared. But the magnitude of dB prime is also the same. dl prime has the same length. It is at the same distance d, because this is also d. And the angle between dl prime and that r minus r prime vector is again 90 degrees, so sine of 90 is 1. Everything is the same in terms of the magnitudes. Their directions are different, but the magnitudes are the same. But so we have these two vectors which make the same angle with the z-axis. So if we sum them up, I just obtain a vector in the z direction. So the total magnetic induction will be basically in the z direction. It won't have any other components. And this will be equal to the integral in the z direction, 1 over c times I, the integral of dl over d squared times cosine of theta, theta 0. This angle is, let's just call it theta 0. I'm just taking the z component, I'm adding only the z components. So that's why I multiply it with cosine theta 0. So B is equal to I over C. Well, along my path, theta 0 is constant, and that cosine theta 0 is nothing but R over D. Then I have that D is constant, so I can take the 1 over D squared also out, so that's D cubed. I have DL, and if I multiply them, if I just sum all the DLs, I get the circumference, which is 2 pi R. In the z direction. So B field is I over C, I times pi R squared over C. I have 2, I have Z hat over D cubed. Well, there is one d squared from the expression for the magnitude of dB. Then I have to multiply it with cosine of theta. And you see, this angle over here is also theta. So cosine of theta is R over D. So that gives me another D. One thing is this factor over here is pi r squared, which is the area of my ring, multiplied by the current in my ring. It's in the z direction. This is usually what we call the magnetic dipole moment. We will come to the multiples in the for the magnetic induction, for the B field later on, but just to kind of a foreshadowing, this is what we will be defining as the magnetic dipole moment. So the B field can be written as 2 over c magnetic dipole moment over d cubed along the direction of this magnetic dipole. Now, just for comparison, the electric field of an electric dipole at a point along the dipole was given by 2d divided by c times d cubed. There are no c's. So they basically have the same expression. So that's why we call it a magnetic dipole. Okay, this d cubed d squared, d is, if you look at over here, d is this the hypotenuse, so it is given by r squared plus small d over 2, that is the height squared. Okay, now let's go back to our problem. So we had already determined what the magnetic induction of a single ring is. So I have one ring over here, the other ring over here. I'm looking at the magnetic induction along this line. This is z is equal to 0. This is the center. This is d over 2. This is d over 2. Let me look at the magnetic induction at that point. Not exactly at the center, but at the point z. Now I will need to modify it slightly. The total magnetic induction, the magnitude, let's say, this will be equal to 2 over c. Both rings have the same magnetic dipole moment. They are both pointing in the same direction. Mu over, well, d is r squared plus d over 2 plus z squared, all to the power 3/2, plus 2 over c mu over r squared plus d over 2 minus z squared to the power 3/2. At this point, this is my point P. So it is distance from the center of the left ring is z plus d over 2. It is distance from the center of the right ring is d over 2 minus z. So you see, this is the expression we have. The B of a ring is equal to 2 over c mu over, well, d was r squared. Let me just call it h squared to the power 3/2. H is the distance from the center of the ring. Now in this problem, since I'm not exactly at the center of both rings, I'm not at the distance d over 2, but just shifted by z from the center. So that's what I'm looking at. And I will be assuming z is small. So I can make a Taylor expansion in z. So first of all, before making the Taylor expansion, is this function odd or even in z? This is an even function. So let's just call it f of z. F of z is equal to f0 plus f double prime at z is equal to 0, z squared divided by 2 factorial plus etc. There is no terms in linear in z. Since f of minus z should be equal to f of z. Only the even powers survive. Do you agree? I'm interested in this coefficient of z squared. Because if I can set it to equal to 0, well, then as a function of z, the magnetic field will be really flat at z is equal to 0. So let's calculate that coefficient. So f prime of z is equal to 2 over c mu times minus 3 over 2, 1 over 5 over second power times the derivative of that thing is twice d over 2 plus z. This is the first, plus the contribution from the other term. You see, the contribution from the other term will be almost identical. The only difference is that the derivative of d over 2 minus z squared will be minus 2 times d over 2 plus z, d over 2 minus z. So the d over 2 terms will just cancel each other. And the z, when I set z is equal to 0, the first derivative will be 0. So that's why I'm not writing it. In the second derivative, the contribution of two terms will be the same. So it's enough to calculate the contribution from the first one only. Now the second derivative at z, and now I will be setting z is equal to 0 also as I'm calculating it. So let's see, these two cancel this two. This is equal to minus 6 mu over c. Well, the derivative of first d over 2 plus z with respect to z is just 1 over r squared plus d over 2 squared to the power 5 over 2. Plus d over 2 plus z, but I'm setting z is equal to 0. Now the derivative of that term is minus 5 halves, 1 over that r squared plus d over 2 squared to the power 7 over 2 multiplied with d over 2, twice d over 2. Now let me just simplify it a bit. So if double derivative at z is equal to 0, this is equal to minus 6 mu over c, 1 over r squared plus d over 2 squared to the power 7 halves. In parentheses, I have r squared plus d over 2 squared. And these two cancel. This one minus 5 d over 2 squared. This is minus 6 mu over c, 1 over r squared plus d over 2 squared to the power 7 halves, r squared minus 4 d squared over 4. They cancel, and this tells me that f double prime of z at z is equal to 0 is 0 if r is equal to d. So this for this condition, this tells me that the magnitude of B along the line connecting the centers will be B evaluate that Z is equal to 0 plus corrections that will be of the order of Z to the power 4. So it will be almost flat. You see, as a function of Z, this is how a parabola looks like. This is how the parabola looks like. If the square term goes to 0, this is how it will look like. So in this region, it is flatter. So you get a larger region which has almost uniform magnetic field. This configuration is called the Helmholtz coils. So this was what you had studied in first year in the lab. Not you, the rest. Now, any questions on this one? Now, another method to create an almost uniform magnetic field is just to, you see, you have these coils. And this is more or less the magnetic field you have. So if you are very close to the wires, such that your distance from one of the wires is much larger than your distance from the other wire, it's almost, I mean, if you are very close, it just behaves like an infinite wire, and you'll get this circular magnetic induction lines. As you are going away, even if you don't satisfy this condition, they are more or less flat. So the magnetic induction, you see, it comes from somewhere from outside the rings. They enter between the rings. As it's trying to get out, the other ring kind of pulls it. And you can just imagine it as if they are pulling it. So it traps it inside this region. So in that region between the rings, most of the magnetic field lines, they just somehow are horizontal. They cannot go out. They just go through one of them and then the other one. But then if you just add more of them, more of the rings will not allow the magnetic induction B lines to leave the region between the rings. And in the limit that you have infinitely many of them, you get what's called a solenoid. So this is basically many rings attached one after the other one. So you have one of them here, just next to it there's another one, another one, another one, etc. And they just make loops. So basically the magnetic field lines inside, they cannot really get out of this solenoid. And so you would end up having B field lines as they are horizontal. Now to calculate these B field lines at an arbitrary point in this region, we will not be doing those integrals, but we can make this observation. You see, we have the curl of B is equal to 4 pi over C times J. Or we can write it as an integral. B dot dl, let me write one more step. The curl of B integrated over any area should be equal to 4 pi over C integral of J over any area. Well, the curl of B, this is some area, which basically implies that if you integrate the magnetic induction over any closed loop, which is the boundary of this area, this will be equal to 4 pi over C times the integral of the current density over that area. But remember, current density is nothing but the current passing, the current passing per unit area. So if you multiply the current density by the area, you get the total current passing through the area. So the integral of B dot dl over any closed loop will be equal to 4 pi over C times the total current enclosed by the loop. Now let's go back here. Well, the magnetic field lines, they cannot leave the region between these currents. So there cannot be any magnetic field lines outside. So B is 0 outside. They are trapped inside. Furthermore, we know that the B lines should be horizontal. So we can just imagine such a closed loop. This is my loop. And I can integrate B around this loop. Let me give some names to the corners, A, B, C, and D. Let's take this to be the Z-axis. Inside B, let me just call it B in the Z direction. Now this X, Y, and Z. No. Or let's say, okay, let's just use the cylindrical coordinates. In cylindrical coordinates, B can only be a function of S. This distance, well, I'm assuming a cylindrical current, so B can at most depend on the distance from the center. It cannot depend on Z. I have translational symmetry. It cannot depend on phi. I have rotational symmetry around the central axis. So the only thing I have is that it can depend on the radial position. So now if you write this integral B dot dl, this will be the integral from A to B of B dot dl plus the integral from B to C of B dot dl plus the integral from C to D of B dot dl plus the integral from D to A of B dot dl. Now from A to B, I will get a contribution. From B to C, along that line, either B is perpendicular to dl or it is 0. In any case, there is no contribution. From C to D, B is 0. There is no contribution. From D to A, B is either 0 or perpendicular to dl, so there is no contribution. And the integral from A to B, let's just say this length is h. The integral from B to D is just B times h. So this should be equal to 4 pi over C. Now the enclosed current, let's say the wire carries a current I, but I don't have one. I have, let's say, n of them in this length h. So the total current is I times n. Now the crucial thing is it positive or negative? You see, the current running through a given area can be both positive and negative depending on which direction it is passing that area. And this one, is it positive or negative? Well, just use your right hand. Just curl your fingers in the direction of the loop. Is the current running in the direction of your thumb or in the opposite direction? Well, in this case, it's running in the same direction, so the current is positive. And so the magnitude of the magnetic induction is 4 pi over C I times n over h. This number n over h is nothing but the turns per unit length, which most of the time we denote it by small n. So although we said that in principle, just from the symmetry arguments, it might depend on S, it just turns out that it's even independent of S. So it's a uniform magnetic field in our solenoid. In fact, whatever the shape of your solenoid is, it will be uniform inside. Although we derive this result by assuming that it is spherical, cylindrical, for an arbitrary shape also. let's see that it will be actually so. Let's assume I have a solenoid of this shape. An arbitrary shape. Well, let's see, I can assume that there is a cylindrical solenoid over here, another cylindrical solenoid over here, another cylindrical solenoid over here, another one over here. I can fill this region with cylindrical solenoids. I can fill it with solenoids with circular cross-section. Well, of course, these solenoids have some currents running also inside my region where there is no current. But look at this point, where I have the intersection of two solenoids. Both of them are carrying currents in the counterclockwise sense. So exactly at that point, one is carrying a current in this direction, the other one is carrying a current in the opposite direction. So even in this system of solenoids, there is zero net current at that point, as it should be. So my initial system of a single solenoid with an arbitrary shape, arbitrary cross-sectional shape, is the same thing as a collection of circular solenoids. On the edge, the net current is what my original solenoid has. Inside, the net current is zero. Each one of these solenoids is carrying the same current, so that they will cancel each other at the inside, and they will give me the overall current outside. And you see, I is the same, N is the same in all of the solenoids. It should be the same. Pi is the same, 4 is the same, C is the same. All of them have the same uniform magnetic field inside. So the magnetic field inside everywhere is just uniform, whatever the shape of my cross-section of the solenoid is. Questions?
On the field lines in this configuration, how do they kind of ages? How do they look like in ages?
In ages? Edges. Well, the magnetic field lines are just, let's say, they will be pointing out. They will be distributed uniformly. No, this is not necessarily uniform, but since the magnetic B field is homogeneous, their lines should be homogeneously distributed. Hmm? So this is another way of creating a homogeneous magnetic field. Yeah, of course, in this case, I mean, it's not easy to put something inside our solenoid and make measurements, make tests, etc. So usually you give a gap. You create a gap, which will basically, the distance of the gap will be equal to the radius of your solenoid. And you have a region of space which has almost a uniform magnetic field in the middle. Yes, any questions before we give a break? Okay, let's give a break, and we will continue after 10 minutes.